All right, in the last video, we reminded ourselves about functions. We got function f of t is equal to t squared. We know that there is a thing called the first and second derivatives, and we know from the power rule that this is what's going to happen. Okay, what we're trying to do is to put these numbers, these functions f, f prime, and f double prime into context as average rate of changes. Okay, and so just as a quick example before we get into a different function, notice that we could fill in the blank here for the velocity or the derivative of the function f of t. And since we're trying to find a blank at a particular time t is equal to 4, you would use the function at 4 plus h minus the function evaluated at 4 divided by h. In this case, h is equal to 0.5, and we're getting something called the average rate of change. So we would get the function at 4.5 minus the function evaluated at 4 divided by 0.5, and you would get 20.25 minus the function evaluated at 4 is 16 over 0.5. And if we compute what that number is on our little calculator over here, we will see what to put in for the average rate of change of the function over at time 4 over a half a second time interval. So you will get 8.5 for that blank. Okay, and then it became important to figure out what was the average rate of change to the average rate of change. Okay, so this blank right here is now in the acceleration column, so it's going to be an average rate of change to an average rate of change. And again, it's going to be the average rate of change, so it's going to be the derivative evaluated at 4 plus h minus the derivative evaluated at 4 divided by h. And in this case, h is going to be 0.5 again, so we would need the derivative of the function at 4.5 minus the derivative at 4 over 0.5. And we would have those numbers 8.5 and 9.5, and then divided by 0.5, and that will come out to be 2. Okay. So here is an example of a function where the average rate of change, the velocity is growing linearly, and the average rate of change to the average rate of change is a constant. Okay. Now that might not always happen, so let's look at another example of a function where the acceleration is not a constant. Okay. So what we're seeing here is a new function. We're seeing in blue, we're seeing the function f of t to be 3t squared. Okay. We are seeing here that the function f prime at t, we know from the power rule, is 6t. And then there is another function here called f double prime at t. Oh, I'm sorry. This is 3t cubed. The derivative is 9t squared, and f double prime at t, sorry about that, f double prime at t is 18t. Okay, so let's take a look and see what's going to happen when it comes to the numbers. So that's how you take the derivatives. Okay, let's see if we can figure out what's going on here with this function evaluated at 1 and the derivative at 1. Okay, so if you were to fill in that blank, you would get f prime at 1, okay, is approximately equal to the function evaluated at 1.5 minus the function evaluated at 1 over 0.5. The function evaluated at 1.5, 10.125. Function evaluated at 1 is 3, divided by 0.5 again. And let's see if we can figure out what number goes in that blank. Okay. By computing our calculator again, 10.125 minus, and you're probably thinking, why aren't we just using the formulas? Right. and we will in just a second, but we need to see what these functions mean in their context. Right, so we're going to get 14.25. Okay, 14.25. Okay. And then let's see if we can understand where this 27 is coming from. Okay, this is in the average rate of change to the average rate of change. So the second derivative evaluated at 1 is approximately equal to the derivative at 1.5 minus the derivative at 1 over 0.5. We're seeing here that our average rate of change at 1.5 is 27.75 minus the derivative at 1, 14.25 over 0.5. And let's see if we get the 27 that we were expecting. So we're trying to compute the second derivative at 1 approximately, and we'll get 27.75 minus 14.25. And we're going to divide by our time spacing h again, which is 0.5. And that's where the 27 comes from. Okay? Now we know that this 27, f double prime at 1, let's see, f prime at 1, we got 14.25, and the second derivative evaluated at 1, we got 27. Now remember, f prime at 1, doing this average rate of change is approximately 14.25, and the second derivative at 1 is approximately 27. Okay. Now we can see that the exact answer for f prime at 1, since we have a formula, it should be equal to 9, right? And not 14.25. The second derivative at 1 is exactly equal to 18, right? So what we're seeing is that we're getting some approximations, and it's those approximations that can become better if we make the time spacing h get smaller and smaller and smaller. Okay, so that's what I want to do in this the rest of this video. Take a look here that I have the function 3t cubed, okay, and I have created a table of values for it, for its average rate of change, the 14.25, and the 27. Those are the numbers we did just a second ago. And you can see that the time spacing is 0.5. So what happens, right, if we try to look at a time spacing 0.1? We could create some values of the function. We could do the average rate of change, again, 11.91, so we would do 5.184, this one minus that one, divided by 0.1, and you get 11.91. If we made the time spacing smaller, right here, can you see what's happening right here? 9.27. We know that the derivative at 1 was supposed to be equal to 9. 9t squared evaluated at 1 is 9. So what we're seeing here is that as the time spacing gets smaller and smaller, this number is getting closer and closer to the derivative at that value, t is equal to 1. Now take a look here, the acceleration, right? The acceleration in this column is no longer constant like it was in the t squared example. Here we were getting the same number for the function second derivative. Okay. Here we can see that the second derivative is changing a little bit. Okay. So let's see if we can understand the numbers that are happening right here. Okay. Notice that the time has gotten closer and closer. The time spacing is getting closer and closer to 0. So what we should see is these numbers 9.27 get closer and closer to 9. This number, as promised, is getting closer and closer to 18. Okay. So that is what makes a function not have a constant acceleration, that we're getting different numbers here in the acceleration column because this function 3t cubed has a second derivative that is not a constant. Okay. So that's what we're seeing here in this picture. We're seeing the function. Blue is the cube function. And then we're seeing the rise and the run. Let's zoom out a little bit. Okay, so we're seeing here at this particular value around 1, we're seeing, right, that the slope of the tangent line is 9. So that's why the red dot right there, the derivative function is 9 at the value of 1. But as you move for different values of x, we can see that the red graph, the slope of the tangent line to the red graph has a tangent line that is going to be changing slope. And that is what this second derivative graph here, the straight line, is showing you, that as you change values of x, the red graph has a tangent line that is actually changing its slope. Okay, so that is another video on the first and second derivatives graphically and numerically. And let me just kind of say what we had done in that table values again. Okay, let me see, did I have this? Yeah. So you could fill in the table of values for the cube function as we did in that video. Try to figure out what is going to go in these blanks. You can see the answers from earlier in the video, what's going to go here. But what we're seeing here is that h is getting closer to 0. And so what these numbers should be getting close to right here, we're at a value 1, so that blank should be getting closer and closer to f prime at 1. And because our function was 3t cubed, the derivative is 9t squared evaluated at t is equal to 1. So that blank right there should be getting closer and closer to 9. And this blank here should be getting closer to the second derivative evaluated at 1, which is 18t evaluated at t is equal to 1, which is equal to 18. So that blank right here should be getting closer to 9, and the second blank should be getting closer to 18. Okay, in the next video we're going to talk about why we're actually having to do all of our videos online, and it is because of these functions called exponential functions. So stay tuned for that one.